Hey everybody, welcome to Mammoth Interactive's YouTube channel. First of all, I want to thank you for watching this video. And remember that this channel doesn't do Patreon. Instead, we sell our digital courses down below. And every single dollar that we get from the products you buy below goes into making more content. The best way to help out this channel and Mammoth Interactive is to subscribe to Mammoth Interactive's huge library of content. Get thousands of hours and hundreds of courses for a low price down below. We have a monthly option and a yearly option. Thanks for listening, and I'll see you in the video.
Hello everyone, and welcome to our machine learning and deep learning course for stocks. In this lecture, we're starting off with our first topic, which is going to be regression. We're going to build several regression models to predict stock prices. But first, we need to talk about what is regression and what is regression used for in finance. And that's what we're doing in this lecture. So let's talk about where the technique of regression machine learning is used in finance. All right, regression is a type of model often used to determine how many specific factors influence the price movement of an asset, such as a stock. These factors can be the price of a commodity, interest rates, industries, sectors, and more. Regression helps investment and financial managers value assets and understand the relationships between variables. These relationships can be, for example, the relationship between commodity price and the stocks of a business dealing in that commodity. With regression, you can predict sales for a company based on different factors like weather, previous sales, GDP growth, and other factors. Regression is used for many types of projects and in many types of industries, not just in finance, but finance does heavily use regression. For example, the capital asset pricing model is based on regression. The goal of CAPM is to evaluate whether a stock is fairly valued when its risk and time value of money are compared to its expected return. This model prices assets and discovers the costs of capital. In this way, it can project the expected returns of a stock. The capital asset pricing model is commonly used because it's simple and allows for easy comparisons of investment alternatives. Now, it's not perfect, no model is perfect, but this is a simple model that works well. With this capital asset pricing model, a stock's returns are regressed against the returns of a broader index, such as the S&P 500 index, to generate a beta for the stock. The beta is the stock's risk in relation to the market or index, and it's also the slope of the regression line. With the capital asset pricing model, the Y, or what you're trying to determine, is the return of the stock, and the X, which is what you use to make your result, is the market risk premium. You can add more variables to the capital asset pricing model in order to get better estimates for your return. For example, you could add market capitalization, valuation ratios, recent returns, and any other factors you want to include to help you calculate the return. There are several types of regression models. We're going to be building several different types. There is simple linear regression, the most basic. There is multiple linear regression, where you use not just one factor, but multiple factors. And then there's nonlinear regression, such as, for example, logistic regression. Here, the visual that you see on the screen is logistic regression, typically used for some kind of binary result, such as, for example, to buy or to sell a stock. So let's talk about the first two types of linear regression, simple and multiple linear regression. Later on in this course, we're going to talk about nonlinear regression. Simple linear regression can be represented with the formula y equals a plus bx plus u, and we'll talk about all of the different variables in there. Multiple linear regression is very similar to simple linear regression, but you just add more factors for x. So instead of just using one factor, for example, the opening price of a stock to predict the closing price, you're going to use multiple factors, like perhaps you'll use opening price, you'll use high price, you'll use volume, etc. So it's just using more factors. The y here in our equation is what we're trying to predict. We're trying to solve for y. So we're trying to predict the y. Typically that would be something like the return of the stock, but it really could be anything that you want to predict about your stock or about your any kind of row that you have, such as could be a stock, could be a house, could be anything that you want to use to make some prediction. For example, in a non-finance example, you could use different features of a house to predict the price of the house. And this can be applied across many industries, financial, real estate, etc. Now, the x is the variable you're using to predict y. X is also known as the independent variable. So for example, x could be the opening price of a stock, or it could be the opening price of a stock as x1, and then you have x2 be the return that you got of the stock on that day or on the previous day. Then x3 could be if the volume increased or decreased. x4 could be whether you bought or sold the previous day. Any kind of factor you want to include in your x. Then we have b, which is the slope of our regression line. A is the intercept, and u is the residual. And that is where regression is applied in finance. Coming up next, we're going to do a deep dive into regression. We are going to build several types of regression models specifically for stock data. These will be some very fun projects, and they will make up the first category of machine learning models that we'll build together. Later on in this course, we'll also build classifiers, neural networks, and more. It's a very fun course coming up with a lot of projects. You won't need to download or install anything to take this course because we're going to be coding in Python on Google Colab, which is a free online code editor. And we will show you how you can get all of the stock data that you need to follow along. And of course, we'll include all the source code for you as well. So join me coming up where we'll get started in our next section. Hello everyone, and welcome to our deep learning and machine learning masterclass for stocks. In this lecture, we're doing a preview of our first of many projects, and that is going to be to build a linear regression model to predict a stock price. We're going to start our project by loading in a data set. We're going to use Netflix stock from Yahoo Finance, all fetched algorithmically, so no CSV files required. Of course, you can extend that to any stock you'd like. We're just using the Netflix stock as an example. Then we're going to pre-process our data for machine learning. So we're going to learn how we can clean it, how we can analyze it, and also how we can split it for training and testing. Then we're going to use a linear regression model to make a prediction. And after that, we're going to be able to visualize the model's results compared to the actual data set. And that way we'll be able to also get an accuracy score of the model. We're going to be able to visualize the results during testing and also during training. Very fun project, very accessible for beginners. So I'm excited to take you through this project. It's straightforward, easy to understand. In order to follow along, you will need some Python programming experience. So be sure to watch the prerequisite section known as Python programming in this course if you have no prior Python experience. Other than that, you don't need any experience to follow along. Also, we will be coding at Google Colab. This is a free online code editor, so you won't have to download or install anything. We'll show you how to get to Google Colab once we get there. So join me in our next lecture where we will get started. Hello everyone, and welcome back. In this lecture, we're going to talk about the machine learning model that we'll build in the next lecture, and that is linear regression. All right, so linear regression is a type of regression which comes from supervised learning, which we talked about in the previous lecture. The main goal of supervised learning is to learn from labeled training data and make a prediction on new data. So regression specifically is where you give your model a training data set of labeled input-output pairs, and X and Y can be any value. They could be, for example, sales versus day. They could be any random Y versus X. They could be the value of a stock versus the date. And each Y is generated by an unknown function Y equals f of X. So Y is dependent on X. It's not just some random X and some random Y. there's actually a relationship between x and y. For example, y could equal 2x, or y could equal x plus 3. And the goal of the machine learning model is to find that relationship. It has to find how it can describe x and y in a relationship. And we're going to see that later on when we build the project. As mentioned, regression is a category of supervised learning, and the goal is to predict a continuous value, not a category, but some continuous value like the price of a house, or the value of a stock, or the size of a bacteria based on the number of days it's been growing. Here is a visualization of linear regression. First, we're going to generate data by creating some function f of x, which could be f of x means like y equals 2x. So you generate data with that function, and then you also apply some noise or some randomness. Then your machine learning model has to find that function. It has to find f of x without you telling it. And next up, let's do a summary. Regression is given a number of features, which is x, and a continuous outcome, which is y. We want to find the relationship between the features of some sample and y in order to make future predictions. So in the future, I could predict what will the price of this house be based on its number of bedrooms, its size, its location, and other features. Or what will the value of a stock be based on its features of opening price and date and closing price. Now, with linear regression, this means we assume that that relationship between x and y is linear. So it is 2x. It's not 2x squared, because that would make it no longer linear. So we're saying the relationship has to be of a linear slope. Linear regression is quite simple. It's a great place for beginners to start. But even though it is simple, it's often outperforming complex machine learning models. So don't be fooled. Even though it's simple, it doesn't mean it's not effective. Sometimes they even outperform nonlinear models, especially when you have small training sets, or you have a low signal to noise ratio, so very little noise, or if your data is sparse, then linear regression is a great choice. Now, the linear model fit by least squares method is what linear regression was inspired by. So it was inspired from a statistical tool from statistics, and of course it was adapted for machine learning. The goal of machine learning and linear regression is to minimize the error of the machine learning model over time. So your model will learn from your data, and it will loop through the data over and over again. And with each loop through your data, the algorithm will improve its accuracy and minimize its error. All right, so now we know what is linear regression, so we can jump into our project. You're going to learn a lot more about regression and machine learning when we actually go hands-on, coming up next. Hello everyone, and welcome back to our course. In this lecture, we're beginning our project of predicting stocks with a linear regression model. We're going to start the project by loading and processing our data for machine learning. So join me at collab.research.google.com. This is the link to a free online code editor where we'll be coding in Python. First steps first, make a new code cell, and we're going to install Yahoo Finance. This is the API that we're going to use to load in our stock data. So I'm going to access the console with an exclamation mark and call pip install y finance. Then I will run this code cell, and that will install this module for me, y finance, so I can access its data. All right, now we have to import y finance into our Colab. Great. Okay, after we have imported Yahoo Finance, we can now use it. So I'm going to grab Yahoo Finance and use its download function. This allows me to download some stock data. Here I have to pass in several arguments, starting with a tickers argument. This represents which stock you want to download. I'm going to create a new variable called my stock ticker. All right, then let's define that, stock ticker. I'm going to use Netflix stock, but you can use any stock you like. NFLX, that is the ticker for Netflix stock. Make sure you have it in all caps because it is case sensitive. Next up, we need to pass in a start argument. This represents the start date that you want to collect. So I'm going to create here start date, and I'm going to pass in 2016-01-01 because I'll get about 5 years worth of data from 2016 to 2021. Note here I'm passing in the year, then the month, then the day. Finally, we're going to pass in an end argument, and we're going to create a variable called end date. So let's define that. This can be any date you like, 2021-01-01 for example. Just make sure it's already passed. All right, and just like that, we'll be downloading our data. The result is going to be a data frame, and we can actually paste out the results that we get. So let's run this code cell and get our results. Look at this. We now have 1,259 rows by 6 columns. The first column is not officially a column, it's known as an index column. It's the date. Then we have the opening price of the stock on that date, the high price of the stock on that date, the low price of the stock on that date, the closing price of the stock on that date, the adjusted closing price, and the volume, the number of trades. Awesome. Now this data frame, we can actually get its type by calling dataframe.info and running this code cell, and you'll see this is actually a pandas data frame. The pandas library is very commonly used in both data science and machine learning, and it provides a way to store a spreadsheet or a table of data in a very efficient and fast form known as a data frame. The data frame also allows you to access a range of functions that are very useful. All right, and just like that, we have loaded in our data. Next, let's define our X and Y from our data set. So I'm going to create a new code cell, and I'm going to define my X, which is typically going to be uppercase, and my Y, which is typically lowercase. So for my X, I can grab my data frame, and I'm going to use the function iLoc or iLocation and pass in here, note the square bracket notation, a colon, comma, 1. Then I'm going to grab the values, and let's paste out X to see our results. So here we've taken our data frame and we've converted it to an array. You can also call x.shape to get the shape of the array. So we have 1,259, which means that we have a one-dimensional array. Similarly, I want to get my Y, so let's create a Y. The X is the independent variable and the Y is the dependent variable. X can be multiple features about some input, like a stock, and Y is what you're trying to predict, typically stock price. All right, so for Y, I'm going to grab my data frame and use iLoc again. This time I'm going to go up to 4, and let's paste out Y. All right, then I can get y.shape and run that code cell. Okay, we have the exact same shape for X and Y, because for every row of X, we must also have a row of Y, because we need to have a pair. All right, now let's reshape our X and Y. We're going to turn them from just regular Python lists, also known as arrays. We're going to turn them into Numpy arrays. So let's create a new code cell and import Numpy. Because we're in Colab, we don't have to install Numpy. We can just import it here. The Numpy library is very commonly used for data science and machine learning because it has ranges of scientific computing functions, and as well it has the Numpy array type, which acts as a wrapper for the regular Python list type, and it allows you to work with arrays much faster. They process a lot faster, and they have more functions that are available. So I'm going to take x and I'm going to override it. I'm going to use numpy.array to create a new array out of x. So it's just going to take the x list and it's going to wrap it in the numpy array type. Then I also want to reshape it. I want to reshape it by the dataset size, or the number of rows. Number of rows, doesn't matter, and by -1. So let's define number of rows. What is number of rows? Well, we just checked out the shape and we know that it's 1,259. So that's what we're going to assign it. Now we can paste out the new value of x, and look at this, it's now multi-dimensional. I'm going to call x.shape and show you the shape. We now have 1,259 by 1. All right, that is what we're going to need for our model, so that's why we had to reshape it. We're going to do the exact same thing for y. I'm going to take y, remember it's lowercase, and use numpy.array to wrap the y list into a numpy array type, and then I'm going to reshape it by number of rows, comma, -1. Then I can paste for you the new entries of y. Great, and we can see it's also two-dimensional because we have these double square brackets. We can see that it's an array of arrays. And we got that array of arrays by using that reshape function. All right, one more thing we have to do to pre-process this data for machine learning is we have to split it into training and testing. So with the machine learning model, you're going to typically train your model on 80% of your data set and then test it on 20%, the remaining 20%, because you want to test the model on data it's never seen before. So you need to split your data set up. Let's do just that. So we are going to import from scikit-learn.model-selection the function known as train test split. So scikit-learn, this is another very popular library for machine learning. It has a lot of different functions and classes, including train test split. So we're going into the sub-library model selection. We're going to use this function to split our data for us. All right, so I'm going to call train test split. I'm going to pass in my x and my y. As well, I'm going to pass in a test size. So that is the size I want for my testing data set. So if we want the 20% of the data to be for testing, that is the same as 2 divided by 10, 20%, or 1 divided by 5. As well, you can pass in a random state. So if you want randomness, if we pass 0, then we won't have a random state. Okay, and the result of this is actually going to be 4 different variables this train test split returns. And if you're interested, you can look in the documentation for train test split to see that. So the result is going to be x train, x test, y train, and y test. So let's break this down. The x train, that is the x for training. X test, that is x for testing. Y train, that is y for training. And y test, that is y for testing. Then I can paste for you all the variables. For example, let's start with x train. And let's run that code cell. And okay, we get this result of an array. It's more interesting to see xtrain.shape because the shape of x train and y train should be the same. The shape of x test and y test should be the same because for every x, we need a y. So look at this, xtrain.shape is 1007 by 1. So we took our initial data frame, which was 1259, and we brought it down to 1007, and the remaining should be an x test. First, let's verify that ytrain.shape is the exact same as xtrain.shape. Great, it is. 1007 by 1, excellent. Then we can grab xtest.shape, can run that. And look at that, 252. So that means that 1007 of our rows or our stock dates, those will be for training, and 252 will be for testing. We can also verify that ytest.shape is also 252. We can also grab xtrain.info. You can run this code cell. But you'll see here, info is for the pandas data frame type. But xtrain is no longer a data frame, it's actually a NumPy type. So we could print out here xtrain by wrapping it in a print function, and that will just give us the values of xtrain. But we can't use functions like info anymore because those were a data frame. Those were of the pandas data frame type, but we're now using a Numpy array type. Awesome. Okay, and that is all we need to process our data for machine learning. Coming up next, we're going to actually begin building a machine learning model, and we're going to use it to make a prediction about stock price. So head on over to the next lecture where we will continue this project. Hello everyone, and welcome back to our course. In this lecture, we're going to use a linear regression model to make a prediction about stock prices. So let's continue on in our collab. All right, first off, we're going to import from scikit-learn.linear-model the linear regression class. So this is actually a pre-built class that contains for us the functionality behind linear regression. So instead of having to write it from scratch, we can just use this class. If you're interested in how the class was built, then just go to the documentation for scikit-learn.linear-model.linear regression, and you can see exactly how it was built. Now let's instantiate our linear regression class. So we're making a new object, and this will be our model. Then we can grab our model and we can use its fit function. This fits the model through the data, and it's the equivalent of training the model because you're feeding it data for it to learn from. What is our data? Well, let's think about this. Currently, what phase are we at? Well, we're calling fit, so we're training the model. So what data do we have to fit the model during the training phase? The answer is we have to feed it the training data, which is xtrain and ytrain. So let's do just that. We're going to feed the model xtrain and ytrain. All right, and the result of this is going to be the model again, but just after it's been trained. Then we can call model, and we can see that it will be a linear regression type. All right, so now what do we do with this model now that it has been trained? Well, next up, we can now use the model to make a prediction. So for that, I'll make a new code cell, and I will call model.predict. So I'm using the predict function, and this time, instead of feeding it the x and the y, I'm actually only going to feed the model the x. Because let's think about what phase are we at now? We're at the predict phase. So this time, we're actually not training the model anymore. We're using the model, which means we are testing the model for accuracy. So instead of feeding it both of x and y, we're only going to feed it x test. Note that we're now feeding it the testing data because we're in the testing phase. So we're only feeding the model the x, and the model will have to give us the y that it thinks would match the x. Then we're going to compare the model's results versus the actual data in y test. The result of this function is our prediction that the model made. All right, and we can paste out the prediction to see what we get. So the result that we get is an array. This array here, it corresponds to the y that the model predicted for x test. So we can actually get prediction.shape. Here we can get that property. You can see we have 252 by 1 because we have a model predicted y for every single x in x test. Next up, we're going to compare the model's prediction with our actual data. So we're going to see how accurate was the model. Because sure, the model made its predictions, but we have to compare that prediction against our actual data set. Because that way we will see, did the model actually make accurate predictions, or did the model go way off and was it incorrect? So that's what we'll find out coming up in the next lecture. We're going to visualize our model's results and be able to compare them with our actual data set. So join me coming up in the next lecture where we will continue our project. Welcome back to our course. In this lecture, we're continuing our project of predicting stocks with linear regression. In this lecture, we're going to visualize our model's results and compare them to our actual data set. In this way, we'll be able to see how accurate was the model. So for this, we're going to be using another helper library. Let's continue on in our collab here in a new code cell. I'm going to import matplotlib .pyplot as pyplot. Matplotlib is a very popular library for building plots and graphs and data visualizations. It has a sub-library pyplot for Python plotting, and we can import it just as pyplot as a shortened name. Now we can use pyplot, and we're going to use the scatter function first. This is going to generate a scatter plot, so it's going to take all of our data points and it is going to scatter them. All right, so what do I want to pass in here? I'm going to pass in my x test and my y test. So here, x test and y test, that's from my actual data set. That's not the model's predictions. This is my actual data that I scraped from Yahoo Finance, and I want to put it on a plot. So I'm going to then run this code cell, and okay, here we have all of the data points. You can see here on the y-axis, we have from 0 to 600. On the x-axis, we also have 0 to 600 because we're plotting our y versus x. All right, now we're going to plot on top of this a line that represents our model. So I'm going to call pyplot, and this time I'm going to use the function plot to create a line. This time I'm passing in x test, but for my y, I'm actually going to pass in my prediction because my prediction is my model predicting x test. So I'm going to take the prediction and pass that in as my y. So this time we're still plotting the same x, but the y is not the actual data. The y is the model's prediction. So we are going to compare the two on the same plot. I'll just rerun that code cell and look at this. Now you can kind of see there's a line going through the data points. I can change the color of the line just by adding a color argument here, for example, orange. And then that will create this orange line going through my data points. So the blue, that represents the actual data set. And the orange, that represents the line that my model created. The model creates what's known as a hypothesis function. So in our actual data set, there is a function that can represent x to y. Of course, the function isn't perfect because we don't have a perfectly linear data set. We have some noise because the features about a day, like the date, they're not going to be exactly even to the price of the stock on that day. Stocks are more volatile than that. So that's why our data is not actually on a perfect line, but the model, the machine learning model, linear regression, it creates a hypothesis function. So it actually creates this perfectly linear slope. Of course, our data doesn't actually have a perfectly linear slope, but it's close enough that the model can make a hypothesis function with a linear slope, this straight line, that fits through the data. It's very similar to a best fit line. I can also call pyplot.figure, and I can pass in here a fig size argument of 10 by 10. That is going to allow me to set a custom size for my figure. For example, 5 by 5, perhaps a bit smaller. Okay, that's not even big enough. Let's do 7 by 7. That allows us to set the size of the figure to make it a bit easier to see. So we can see now more clearly that all of our data points are somewhat linear, but there is a bit of variation because we can't expect x to y to be perfectly linear. That's not realistic for any real world data set typically. But our model is going to create a hypothesis function that is close enough. So that's that orange line. And that is how we can compare the model's prediction to the actual data set. So our model did quite a good job of building out the line. If the line was completely off from the data set, then we know that something went wrong. Because if our line did not fit through the data, then that means something went wrong and we weren't able to find an accurate hypothesis function. As well, we can also get a score from our model. This will tell us the proportion of accurate predictions or accurate results. For that, I'm going to grab my model and call the score function. And I'm going to pass in here x test and y test. So look at this. For the predict function, we only passed in x test. For score, we're passing in x test and y test. Can you think why we might be passing in both of these arguments into the score function? Well, the reason is that for the score function, we need to compare the model's prediction with y test, the actual labels. That way we can compare where the model was right and where the model was wrong. If I run this code cell, look at that, I get 0.998. So that is almost 100% accuracy, which is quite high of an accuracy. Now, very similarly, we can also visualize the training results. So we can visualize not just the testing phase, but also the training phase. To do that, we'll just follow a very similar process. In fact, we could extract it to a function if we wanted to optimize the code. We're going to call pyplot.scatter again. This time I'm passing in xtrain and ytrain. So again, I'm making a scatter plot using my actual data, this time my training data, not my testing data. I can also pass in here a figure size. So I can grab here pyplot.figure and set the fig size to 7 by 7 again. And I can call pyplot.plot then to plot xtrain. Now, how do I plot the training predictions that my model made? How do I plot the predictions my model made during training? Well, the answer is we can get our training predictions by grabbing the model and calling the predict function again, but this time passing it xtrain instead of xtest. So yes, we can do that. That will give us the predictions during training. And we can pass those into the plot function. Then we can pass in a color here for this line. Otherwise, the default will always be blue. So let's do red. Then I'll run that code cell and look at this. Now we have a lot more data points because remember, we used 80% of our data set for training and 20% for testing. So we have a lot more for training. And look at that. Again, we get that best fit line. And again, we can get a score even during the training phase. We just have to call model.score, and this time we're passing in xtrain and ytrain instead of xtest and ytest. And look at that. Again, the scores were quite high, almost 100%. Hello everyone, and welcome back to our course. In this lecture, we're starting a brand new project where we are going to predict stock price using polynomial regression. So in this lecture, we're starting off by giving you a project preview. First, we're going to load in and pre-process our data for polynomial regression. We're going to be able to analyze it and visualize it. We're going to be using stock data. And of course, you can use any data set for any stock you'd like, or even another data set that's not even stock related. But we're specifically going to be using stocks in this project. Once we have pre-processed the data, we're then going to use it to make a prediction with different coefficients and complexities of polynomial regression. It's still regression, so it's similar to linear regression, but this is a different machine learning model because it's polynomial regression, so you can have higher dimensionalities of regression. And you'll find out exactly what that means coming up. As well, we're going to be able to find the best polynomial model of different coefficients. So we're going to be able to calculate the error of different polynomial regression models to find out which one is the best for our specific data set. Join me in our next lecture where we will get started. Hello everyone, and welcome back to our course. In this lecture, we are going to begin our project of predicting the stock market with a polynomial regression model. Our first step is going to be to load in and pre-process our data for polynomial regression. All right, so join me at Google Colab where we will get started. First, we're going to have to call pip install yfinance to install the Yahoo Finance API. This will allow us to fetch stock data from Yahoo Finance. Once that has all been installed, we can then call import yfinance to use the library here inside of our Colab. We're going to call yfinance.download to download our data. We have to pass in a tickers argument. We're going to use a stock ticker. We can choose any stock we want. For example, I'm going to choose Ethereum stock with the symbol or ticker ETH. We We also have to pass in a start, which is going to be the start date that we want for our data. Let's see here, start date. We're going to define 2016-01-01. We can also pass in an end here, which is our end date of when we want the last day to be that we fetch. Let's declare end date. We can do 2021-01-01. That will give us 5 years of data. The result is going to be a pandas data frame containing that stock data. So we can paste the data frame to get its values. Okay, here we go. And the results are, we have 1,259 rows by 6 columns where we have information about the stock. Its open price, high price, low price, closing price, adjusted closing price, and volume of trades on a given date from 2016 to 2020. All right, and next we are going to now add some more columns here for this data set. So let's create a new code cell here, and I'm going to grab my data frame. I'm going to create a new column here that we will call increase or decrease. So we can actually put whether the volume increased or decreased on a given day. To do that, I'm going to use the Numpy library. So make sure you do import the Numpy library in order to use it. I'm going to use Numpy and set a condition that I'll create a Numpy entry where a certain condition is met. So I'm going to grab my data frame and find where the volume of the previous day with shift -1, that will give me the previous day, where that was greater than the data frame at volume of the current day. If that condition is true, then we're going to put in the value 1, otherwise we'll put in 0. 1 means that the previous day's volume was greater than the current day's volume, so there was a decrease. 0 means that there was an increase. So you can also do it the opposite way, flipped. I'm just going to say here decrease over increase then, because decrease is 1 and increase is 0. As well, we can also write a column that will determine whether or not we should buy or sell. So let's create a new column in the data frame, and we'll call this buy or sell. We'll use Numpy again to find where the data frame at the closing price of the previous day with shift -1 to get the previous row, where that was greater than the data frame at the closing price today. So if the price dropped because the closing price was greater yesterday than today, that means that we can buy these stocks. So we'll put in a 1, otherwise we'll put in a 0 for sell. As well, we can calculate returns. So at the data frame, we can create a new column called returns. To do that, we'll grab the data frame at the closing column, and we'll use the %change function, and that will give us the change between the previous day and the current day automatically. All right, I can then paste data frame to see the results. And look at this, we now have more columns here that have been created. We have volume decrease or increase. So we have a 1 if the volume decreased and a 0 if the volume increased. We have buy or sell. So if the price dropped, then that means that we should buy. If the price increased, however, that means that we should sell. All right, and as well we have returns here, which is just taking the closing price, and it's going to use that to calculate how much you would have lost or gained that day. Awesome. Okay, you'll notice here the first row has not a number because we can't calculate returns on the first day. There's no previous day. So we have to drop that not a number value. We don't want it messing up the data set. Often you'll find that when you're fetching data, you'll have missing data such as not a number or no or none. And so you do have to clean the data of these null values. To do that, we have to just grab the data frame and override its value using the drop NA function that's going to drop any null or not a number values. So that just got rid of our first row because that was the only one that had a not a number. But in other data sets that are more messy, you could definitely find yourself having a lot more null values. All right, and that's how we can create some more columns. Next up, let's now split our data set for training and testing. So from scikit-learn.model selection, in this library, I'm going to import the function train test split. We're going to use 80% of our data for training and 20% for testing our machine learning model. So we will call train test split, and we'll pass in several arguments here. First, we need an x and a y. So what will be our x and y? Well, let's define them. Let's start by defining an x. An x is the features or the independent variable about a date that will help us predict the y, typically the price. So we can use any of the features that we want to try to predict the adjusted closing price is typically used as the prediction. We could use volume, we could use open, high, low. If we had other columns as well, we could use volume decrease or increase, buy or sell, returns. We could also use multiple columns in one x as well. Let's start with just one. So we'll grab our data frame and let's use one of our columns like open. And we'll grab its values, meaning we'll get a list. So that means we'll have x, which is going to be a list of values from the open column. And in fact, I can paste that for you so we can see what x is. Here we go. X is this array of values. It's just taking all of the opening prices and putting them into a list. All right, now for y, let's define y next. Y is going to be from our data frame. Typically, it's the adjusted closing price dot values because that's what we're trying to predict, and we're going to use other features of the date to predict what is the closing price adjusted of the stock on that date. Currently, we're only using one x, but often you'll find yourself using multiple features inside of one x. Currently, we only have one feature per x. Okay, so those are going to be our x and y. We also have to pass in a test size. We'll do 1 divided by 5, which is 20%, which means 20% of our data will be for testing. The result of this function is actually going to be 4 variables. We're going to get x train, x test, y train, and y test. So we have these 4 different variables returned. We have the x for training, x for testing, y for training, and y for testing. All right, and we can already plot our values to get an idea of what our model looks like. So we're going to import matplotlib.pyplot, which is a plotting library. We'll import it as the nickname pyplot. And we can use this to visualize our data and see what trends we have, because that will give us an idea of what kind of machine learning model, like what kind of regression can we perform on the model. Because if the model has a certain trend, that gives us a hint of what we can do. So I'll call pyplot.plot, and I am going to plot x train and y train. All right, then I'll run this function, and let's see. Oh, we just have to make sure we ran the previous code cell before we run the second code cell, because by default, values won't be actually created if you don't run that code cell. Okay, so the result we get is a bunch of these lines here. I'm just going to add a string bo to the plot. That's going to put everything into dots instead of into lines. All right, and that is our training data plotted. So we can see here, it has a relatively linear slope, but we are going to perform polynomial regression, which means we can have nonlinear slopes, just so we can learn how to do that. Okay, as well, we can plot our testing data. So we can call pyplot.plot x-test, and we can plot as well y-test. Again, I'm going to pass in bo here. All right, that's our testing data. Note that it's slightly less dense because there's only 20% of the data set here for testing, and 80% was for training. As well, we can also plot the density of our values, for example, for training. To do that, I'll call pyplot again in the same cell, and I'll call plot. This time, I'm going to plot here xtrain, numpy dot zeros like the xtrain. All right, then I will run that code cell again, and here we get this line. All right, that line, this represents my distribution of data. And if I put in another string here, r plus, this is going to show me here the density of the data points on this red line. I can also do the same for the testing here. I'll call pyplot.plot, pass in xtest, and a numpy.zeros like the xtest. This means that we're taking xtest and we're creating a numpy array, or a list of zeros that is the same length as xtest. That's just what we're doing here. And that is the equation for being able to calculate density. I do have to also pass in here r plus, lowercase. Then if I rerun the cell, I will have the number of data points being shown as well. So you can see we have some distribution. Sometimes it is a bit heavier than at other locations. Awesome. And just like that, we have prepared our data for our polynomial regression. So join me coming up in our next lecture where we will begin. We will make a prediction with a polynomial regression model. Hello everyone, and welcome back to our course. In this lecture, we are continuing our project, and we're going to make our first prediction using a one-dimensional polynomial. All right, so for that, we can first start with linear regression, which we did previously. Because polynomial regression builds upon linear regression, it just takes the equation for linear regression, which follows the formula y equals wx plus b, and it allows you to add greater coefficients like wx squared or wx cubed. We're going to start with linear regression. All right, so that would be a polynomial of degree 1. So I'm going to import from scikit-learn.linear-model the linear regression class. Then I'm going to instantiate a new linear regression model. We did this in our previous project as well, and this is also known as a one-dimensional polynomial. So you'll recall we have to call model.fit in order to train our model. Then we're going to pass in our x training data. We do have to reshape it though to -1 by 1 in order to give it an extra dimension. All right, and then we're going to pass in our y train that will fit our model through our x and y data. Then we can take the model and use the predict function, and we're going to pass it xtest.reshape -1 by 1. The result will be our model's predictions. Then we can paste out predictions. I'll run this code, and we get this result. All right, now we can do the same thing with a one-dimensional polynomial. So for that, I'm going to add a new code cell. I'm going to call numpy. So I'm going to have to use the Numpy Library, which I imported earlier. And I'm going to use numpy.the poly1d function. This will create a one-dimensional polynomial. And into here, I'm going to pass in numpy.polyfit. This will allow me to fit a polynomial regression line through my data. I'm going to pass in here my x train and my y train data, as well as 1, which is the coefficient of the polynomial. If the coefficient is 1, then you just have a one-dimensional polynomial, which is the same as linear regression. I'm going to save this as my model 1D polynomial. Then I can use that model of a one-dimensional polynomial and pass it xtest. The result will be my model 1D predictions. Then I can paste those out, and we'll see that we'll get exactly the same values as we did for our linear regression. So I can get here, for example, the first 5 values from linear regression, and I can get the first 5 values from one-dimensional polynomial regression, and you'll see they're exactly the same. That's because one-dimensional polynomial regression is exactly the same as linear regression. Coming up, we're going to learn how we can make higher dimensionality polynomial regression. So join me in the next lecture where we will work on that. Hello everyone, and welcome back to our course. In the previous lecture, we learned that a one-dimensional polynomial regression model is exactly the same as a linear regression model. Coming up, we're going to, in this lecture, create higher dimensionality polynomial regression models. Let's start by making a two-dimensional polynomial regression model, which has the formula y equals mx squared plus b. So that two-dimensionality comes from changing that x into x squared. All right, so I'm going to create a model 2D polynomial this time. And I'm going to use numpy dot poly1d again, but this time I'm going to pass in numpy dot polyfit, and I'm passing in x train and y train, yes, but the coefficient is different. It's now going to be 2. So let me just extract this into my coefficient 2d, which will be 2. Then my coefficient 1d was 1. So I'm just going to make that a constant so it's clear what's actually being passed into that function. Okay, great. And that is going to pass x train, y train, and our coefficient. So now we're going to be performing two-dimensional polynomial regression, like a parabola. So for this, I can then make a prediction by making model 2D predictions this time. And I'm going to grab my model 2D polynomial, and I'm going to pass it x test. Then I can paste out the model 2D predictions. I can get the first 5 and compare the results. So you can see here the results are slightly different from one-dimensional polynomial regression. Now, how do we compare the two? Well, we can use an error metric to compare which one had the higher error. So I'm going to make a new code cell, and here I'm going to use mean squared error. Mean squared error is one of many different types of ways to calculate the error of a model. We have to import from scikit-learn.metrics the mean squared error function. This has all the functionality behind that calculation of the error. And then I'm going to be able to call that function. So I'm going to call numpy.squareRoot to get the mean squared error, and then I'll square root it, so that leaves us with the error because we're square rooting a square. And I'm passing in here y test, which is my actual y, and I'm comparing it with my model 1D predictions. Then I can run this code cell, and this gives me the root mean squared error, 73%, which means that my error was 73% for my 1D predictions. But let's compare that with numpy.squareRoot, so the root mean squared error of our two-dimensional polynomial. So I'm going to call mean squared error again and pass in my actual y test from my data set. And then I'm also going to pass in my model 2D predictions. Then we can run the code cell, and look at this, the error is slightly less. Now we can create our higher degree polynomials just by increasing our coefficient value. So let's put on another one, and then we can graph all of our results. We have currently just a line, which is one-dimensional. We have a parabola, which is 2 dimensions, so x squared. We can also make a nonic, which is going to be a graph of the 9th dimension, with degree 9. We could make degree 3, 4, 5, 6, 7, doesn't matter. We can just keep increasing. Let's choose 9 next. So for this, I'm going to call numpy.poly1d and then wrap in numpy.polyfit my x train, my y train, and this time my coefficient. Let's see, coefficient is going to be for 9D. So we're jumping up quite a bit. I'm going to make coefficient 9D, and then later on in the next lecture, we're actually going to try a whole bunch of more coefficients and compare all of them. Okay, the higher the coefficient, the more curves in your graph. So let's now calculate the error of this third model that we have, which has coefficient 90. So first we need to store this polynomial. We're going to call it our model 9D polynomial. Great. Okay, then we are going to use that model to create a prediction. So we'll call model 9D polynomial, and we are going to pass it, or yes, we're going to pass it our X test. The result will be our model 9D predictions, and we can get the first 5 values from that, just like we did for 1 dimension and 2 dimension. Then we can also calculate the error by calling numpy dot square root and getting the mean squared error of y test compared with our model 9D predictions. Then we can see, okay, the error is 61%. Awesome. Okay, now we've tried out several different models, but how do we determine which one is the best? Because there's so many coefficients that we could try. Well, coming up next, we are going to take a range of values. For example, we could go all the way from coefficient 1 to coefficient 9 and test every single coefficient, 1, 2, 3, 4, 5, 6, 7, 8, 9, and even further than that if we wanted to. And what we're going to do is we are going to compare the error during training and testing of every single one of those. That way we'll be able to know which one had the smallest error and therefore which one is the best one to use. So typically you'll test out a whole bunch of coefficients, and then after that you'll be able to see which one was the best performing, and that is the one you actually select to use and to deploy or to use in production. So join me coming up next. We're going to finish off this project by finding the best coefficient.
Hey everyone, thanks for watching this course. If you want to watch the rest of the course, the link is down below. Not only will you get the access to this course, but you'll get access to a lot of other courses in a huge bundle, and it's on sale today. So buy before the sale ends. Thanks for watching, and I'll see you in another video.